All right, so we're getting closer to the end now. So today what we're looking at is scheduling problems. So when we got scheduling, we want to schedule a job. Um, Usually there's things that you got to take into account: time that it takes to do each task in the whole job, and also the order that they need to do. So, you're making a chair, you can't assemble the chair before all the bits are made. And then to make all the bits, well, some bits might be fiddly, so they might take a bit of time. Other bits are not going to take as much time. So we need to schedule, or we need to order it. And so we can have the information in, say, a weighted activity table. All right, like this one down here. I'm going to use this example here throughout this. Now, as usual, I forgot to mention this at the start, as usual in the notes on physics with Synno, there's more detail in the steps written out that I go through than I'm going to put in here. All right, so weighted activity table, there it is, activity A, takes 8 days in this case, but then there's nothing, so it can start. Activity B, again, there's nothing before that, so A and B can start together, and then after that, then we follow on. And so that, of course, could be in an activity network. All right, and so the activity network of these things here is this. So here, so at the start, A takes 8 days, B takes 6 days, and away we go. And then we do certain things. So in this one, we've had to put in a dummy, because I guess before C's got to happen before F can start. Let's have a look. Yep, C's got to happen. All right. So we've got a dummy there to make that link. Now you'll notice, of course, that any dummies, have a weight of 0. All right, so they're not an actual task that's got to take place in the whole job. All they are is looking at the pathway, the sequence. So the dummy doesn't take any time at all. The time that it takes is the 1 hour before the C there. All right, so then there's what we would call things. Sometimes there's things that call float time. So I'm going to just draw a simple activity network here. So here's the start. We're going up here to there. We're coming down here to here. Then we're going here to our finish. And then we're going across there. That's A and it takes 5. This is B and it takes 3. This is C and it takes 6. And this one here is D and it takes 2. So before D can happen, it's got to have A and B and then C. All right, before they can happen. Now, when we notice this, if we're going around this way, around there, A plus B is 5 plus 8. 5 plus 3, which is 8. However, if we're just going across here, that's just C, which is 6 hours. And so you'll notice that there's a difference here in the amount of time. Now, given that D has got to have all of those things happen before it can start, D has got to wait. We can't start tasks D for 8 hours after starting A. all right, because it takes 5. If this is hours, it takes 5 for A, then another 3, so it takes 8 hours before you get to this point. However, C takes 6, so what we've got here for C is we've got what we call a float time. Because C, the starting time of C, is not overly critical. It doesn't have to start as soon as A starts. It can start anything up to 2 hours later. All right, so, and I get that by 8 minus 6 equals 2. So anything up to 2 hours after A starts, C can start. We don't want to start longer than 2 hours because then we're waiting for C to finish. And then that's not very efficient because we want it looking for the shortest times we want for efficiency. All right, so that time that C can kind of hang around is called the float time. So then we get into things what we call the earliest start time. All right, so when we're looking at things, so that's the earliest start time is the earliest a task can start. And when we look at this thing up here, for D, the earliest that D can start is 8 hours after A started. All right, because we're going around here. So it's D starting's determined by these. So the earliest it can start is 8 hours. However, C again, there's float, and I'll get to what the float, but the earliest time for C would be start exactly at the same time as A. That's the earliest it could start. We wouldn't want C starting before A, all right, because then we're hanging around. All right, more to do that when with the example. And so the way we do this, I've left a hole. That's because it doesn't fit. A thing called forward scanning. So a process called forward scanning. So forward scanning, what it does is it scans forward. All right, so here's our example. All right, up here, activity network of it. Weighted table, activity network. And so here's what we've got. Now you'll notice that what I've done here is I've put some boxes. All right, it's got some boxes here. And these boxes are split boxes, so they've got 2 bits to them. All right, here we go. Beautiful. There's our boxes. And so what we're going to put in these boxes will be what we call the earliest start time. And we'll use them again when we get up to it for what's called the latest start time. But the earliest that we can start a task is what we're looking for. I'll just finish these nice squares here, boxes. Beautiful, beautiful. Now I'm going to change my color. Let's go to orange. Beautiful, hasn't changed that. All right. So we draw the split boxes and then we look at, all right, so the earliest we can start is time 0. And the same here for this task here to across there. That's B. All right, so the earliest they can start is bang, straight at the same time. So now we're looking at time from the start here, right? So it's time from the start. So the earliest C can start is after A is finished, which is 8 hours. Or 8 days, I should say. 8 days from that thing up the top there. I won't scroll back. Excuse me. Then C happens, but the earliest E can start, C has got to finish. But C couldn't start from 8 hours after the start here. So the earliest E can start in relation to the beginning is another hour longer, 9 hours. All right. Then we go 3 down here, another 3 hours. So the earliest that we can start is 12 hours. And I'll put that there because we can come this way as well. And so let's have a look and see coming this way what happens. If we come this way, we go, all right, 6, another 2, 8, another 1, 10. That's 10. Or we can get to here with this dummy. So 9 plus the 1 again is 10. So the actual earliest start time out of this 12 and this 10, the earliest time G can start is 12 days after the beginning. All right? And it's determined by this longest time around here. All right? We can bang go around there 10 hours or 10 days, but you can't start G till you get this stuff, which is 12 days. So that's all right. Then we'll just move. Earliest it can start H is two days later than there, so 14, and then another 1 day here. So the earliest time that we can finish this job, or the shortest time that for the project to take, is 15 days. So our project takes 15 days. All right. Now, in some of those things, there's going to be, excuse me, in some of these things, there's going to be float times, all right? So, like around here, for example, only takes 10 days. So there's a whereas around this way it takes 12. So there's a 2. Actually, I made a mistake there. I think that should be 9. That one, I have made a mistake. 6 plus 2 is 8, but F can't start until C's finished, and that's 9 around there. So that one there should be 9. I made an error on that one. Hopefully that doesn't confuse you. So just going through again, remember F can't start until C's done. And it takes 9 days for C to finish. But it only takes 8 days for those. So it's got to be waiting around here. So there's some, what we call some float times in some of these things. All right, so the float times then bring us to what we call the latest start time. Excuse me, it's not for the whole job, the latest start time for each task. I hate it how it does that. So for each task. So some can start later if there's a float time. So if float time could start later. And what we look at is we look at backward scanning. So with the backward scanning, what we do is we are at the finish and then we move forward. And so I'm going to change my, whoops, wrong one. Going to change my pen color again and use a different color for my backward scanning. How about a nice crimson-y one? I'll have a bit of a drink here. All right, so let's have a look. Takes 15 days, so 15 in there. then when we come back here, back this way, 1 hour off, or 1 day off, 14 days. Come back here, 2 hours off, 2 days off, there's 12 in here. All right, then when we get, so let's go around this, I'll go around this way. All right, so when we go this way, 12 take 3, 9. 9 take 1, 8. 8 take 1, 0. But what about if we go around the other way? 12 here, 12 take 1 is 11. Then, when we come down here, 11 take 2 is 9. 9 take 6 is 3. So you notice that with some of these things, these ones here, there's float times. Because there's a difference between their earliest start time and their latest start time. So for this one here, we've got a 2-day float. All right. So F can start anything up to 2 days before G needs to start. All right, this is what that means. So critical path. We've got critical path, critical path. So thing for critical path is that's the path. I hate it how it jumps like that. So it's the path with 0 float times. Now you can see that I've already up here done that. So 0 float times here to here. So we've got to go around that way. 0 float time across there. So our critical path then is A, C, E, G, H. So for this one, I'm going to write it up here so where we can see it. So our critical path is A, C, E, G, and H. They're the ones that determine how long the whole job takes. These other things here, B, D, and F, they can float around a bit in there. All right, and as long as we keep them within the constraints of our critical path, our job will still finish at the same time. All right, so we can represent those, that critical path. We can represent that again in a table. And so here's our table. So I've got my earliest start times and my latest start times there in which I've got from my network. So here's my original table, and so out of these things I grab them out of the network, so these numbers are out of here. All right, and so for A, 0 and 0, for C, 8 and 8, and so on. All right, and so what we then do is we look at the float times, and so there's some float times which are 0, and so they're the critical ones, and I've put them with the asterisks. And so when we look at down through our thing, first asterisk is with A, the next asterisk is with C, one after that's E, G, and then H, all right, which is exactly what I got here from the network. All right, so there's two ways we can do it: the network and the table, and critical path is 0 float times. All right, so as I already mentioned, if you want more detail in those steps and things, the notes on Physics with Synno, they have it there, and so you can download those PDFs off Physics with Synno. All right, as always, have fun, and if you need some help, get back to me.